The first thing that we're going to talk about today is source combinations. So let's start by looking at voltage sources in series. So can somebody provide me with an example of where you might connect voltage sources in series in real life? Yeah, changing the batteries in a remote control is, if the remote control requires more than a single battery, is literally an example of combining voltage sources in series. Okay, so generically speaking, we might have a system like so. So we would have some voltage source VDC1 connected to some voltage source VDC2 connected to some sort of resistive element R connected to, let's just say it's a third voltage source like so, VDC3. Okay. So I'm going to define the voltage drop across my resistor as positive polarity on the left, negative polarity on the right, like so. And I'm just going to call this VR. There is no rhyme nor reason to why I chose positive polarity on the left, negative polarity on the right for this one. Just what felt right to me. So if we apply Kirchhoff's voltage law around this loop, what we will have is negative VDC1 plus VDC2 plus VR minus VDC3 is equal to 0. And what I'm going to do is I'm going to leave VR on one side of the equal sign by itself and put all of those DC voltage sources on the opposite side of the equal sign so that we would get VR is equal to VDC1 minus VDC2 plus VDC3. And I'm going to say that this is VDC equivalent. That looks like a G, not a DC comma. So DC comma equivalent. So the resistor in this network sees an equivalent DC voltage source that is a combination of all of the DC voltage sources that were connected in series. Now, I want you to notice that voltage sources that have the same polarity were added together. So that's VDC1 and VDC3. And the voltage source that was the opposite polarity was subtracted from that combination. Now, when I'm looking at polarities for voltage sources, what I'm really doing is effectively imagining a current flowing around this loop, either clockwise or counterclockwise. And all of the voltage sources where the current hits the positive polarity terminal first are added, and all of the voltage sources where the current hits the negative polarity terminal first are subtracted, or something like that. That's how I'm looking at polarities. So if we followed a current around our circuit in a clockwise direction, we could see that VDC1 and VDC3 have the same polarity because the current would be hitting the negative polarity terminals of those guys first. VDC2 is of the opposite polarity because it hits the positive polarity terminal first, and our equivalent DC voltage is just the difference between all of the ones where it hits the negative polarity terminal first minus the ones where it hits the positive polarity terminal first. So for those of you who may have put a battery into a battery pack or something like that backwards and ever wondered why the remote cares, well, if you have two AA batteries in a remote control and you put one of them in the opposite polarity, the voltages of those two batteries cancel each other out. There is no voltage being applied to the circuit, or a very small voltage, because the chance of the two batteries having exactly 1.5 volts is effectively zero. But anyway, there's not enough voltage being applied across the terminals of the circuitry inside the remote for it to ever work. Same kind of situation when you put batteries in your battery pack backwards, right? So you just simply have voltages cancel each other out instead of adding together, and you're messing with the electrical network. So voltage sources in series is fairly straightforward because we've all probably done it at some point, as you know, we've had to change the batteries in something. Although for whatever reason, we're rapidly approaching a point where we don't get to change the batteries in our devices anymore. Like back in my day, I'm gonna sound like an old man, you used to be able to, you know, take the battery pack out of your phone, replace it, this, that, and the other. Nowadays, it's all embedded in there. I'm a firm believer in right to repair, but anyway. So here's voltage sources in series. Any questions? All right, so now let's look at something that's maybe a little less obvious, but it happens all the time. So voltage sources in parallel. Okay. So can anybody think of an opportunity where we might see voltage sources that are connected in parallel? Anybody got any? Yes, sir. Maybe.
Stuff plugged in the house.
So that's a really good thought. So every single outlet that you see in this classroom, and practically every single outlet that you'll see in any sort of residential or commercial place, comes in a pair. So that's what's called a duplex receptacle, where each of those two things are wired in parallel. So that is a pretty good example of a voltage source in parallel. Another one that may be less intuitive, but is done very, very often in industry, particularly in solar installations, would be how you wire up solar panels for your home and all of that kind of good stuff, right? So let me just draw a simple, terrible system here, okay? So let's say that we have this diamond shaped looking thing is supposed to be a solar panel, okay? Actually, let me move that down so I can draw some leads. So we've got a solar panel, and let's say that this is panel number 1, and it's rated for 12 volts and 1 watt of power, okay? If we had a second solar panel, like so, this guy is also rated for 12 volts and 1 watt, and we connected the positive polarity terminal of one to the negative polarity terminal of the next, we would have voltage sources connected in series, right? So what would be the voltage seen across those open circuited terminals on the right-hand side of the page, or the right-hand side of the network? So each one of those panels counts as a 12-volt source, and they're wired in series. So what's 12 plus 12? I feel like it's 24. Okay. So we would wire these solar panels in series to boost the voltage in the system. But we might also add in a string of parallel connected solar panels, like so. So here's number 3, also rated for 12 volts and 1 watt. Positive polarity terminal and negative polarity terminal. And here's a 4th solar panel, like so. Also rated for 12 volts and 1 watt. Okay. So the voltage drop across those open circuited terminals on the right-hand side would still be 24 volts according to Kirchhoff's voltage law, right? So why would we ever add that second string of panels in parallel like that? Well, adding the second string of panels is going to boost the overall current and the overall power that the solar panel array can deliver. So you'll usually see some combination of series and parallel connected solar panels in any individual solar array, with the goal to provide the correct voltage for whatever application you're looking at, and then you put your strings in parallel to boost the current. So outside of Louisiana Tech, I do some work for a company called Sabre Industries over in Bossier City, Louisiana. And we design lithium-ion battery energy storage containers that are used in conjunction with solar arrays. How many of you guys have ever seen the pictures of the huge solar array out in the middle of the Mojave Desert? A couple of you guys have, okay. Might be interesting for you guys to know that some Louisiana Tech students and myself, as part of our work with Sabre, actually designed the battery energy storage that goes along with that giant solar array to serve the Los Angeles Water and Power District. It was a multi-million-dollar thing that we did probably, I think it was 5 years ago. We worked on it. So anyway, so as part of my job at Sabre Industries, I design these battery energy storage systems where effectively we might have 22 racks full of batteries providing somewhere in the ballpark of 1500 volts, but we wire them all in parallel so that we can get tens of thousands of amps out of these batteries. So we design systems, 1500 volts is what we would consider in the industry a medium voltage, but we're able to produce megawatts of power out of these battery energy storage systems to be able to help large municipalities like the city of Los Angeles ride through blackouts and all of that kind of good stuff. So anyway, voltage sources in parallel are a very, very common practice in industry, particularly more now than ever because of all of the renewable energy sources that are being integrated in our utility grids across the country. So with that context out of the way, now let's talk about the circuit analysis techniques to look at these things. So realistically, we have to be pretty careful when we're dealing with batteries connected in parallel. So let's say that I have some DC battery or voltage source, VDC1, and I'm going to explicitly give this a numerical value of 5 volts. Then we have some resistance here. Let's just call it a 10 ohm resistor. And on the opposite side, I'm going to have a second DC voltage source. And let's call this 5 volts as well. So in this simple system, we have two 5-volt sources and a 10 ohm resistor connected in parallel. And I'm going to define the voltage drop across my 10 ohm resistor as VR. So if I were to apply Kirchhoff's voltage law around this loop, what I would find is that, so let me do KVL at the blue, I would get negative 5 volts plus VR is equal to 0, which means that VR has to be 5 volts. Pretty straightforward. Very similarly, I could do KVL around this loop. And I would have negative 5 volts plus VR is equal to 0, which means, once again, VR is equal to 5 volts. And lastly, I could do KVL around the outside like this. And I would have negative 5 volts plus 5 volts is equal to 0. All three of these check out, make sense under the context of Kirchhoff's voltage law and what we know. But I can break this system by doing something like this. Okay. So if I put a 5 volt source on the left, my 10 ohm resistor once again here in the middle, across which I have some voltage VR. And then I put a 4 volt source on the right hand side, things break down, okay? So if I do KVL around the left hand loop, what is VR? 5 volts. If I do KVL around the right hand loop, what is VR? 4 volts. They should be the same thing. So how is 5 volts equal to 4 volts? Or thinking about it in the context of doing KVL around the outside, negative 5 plus 4 does not equal to 0. So if we ever have voltage sources connected in parallel that do not have the same voltage, we actually can't apply our circuit analysis techniques. So could we construct a circuit like this on a physical breadboard? Absolutely. There is nothing whatsoever stopping me from connecting two batteries in parallel that don't have the same voltage drop across them. What do you think is going to happen in practice? So effectively, because in a real system, our wires have some amount of resistance, it's usually small, but it is some, we will see that that wire is effectively going to have to absorb a whole bunch of power in order to try to balance this system out, right? So the voltage drop across a wire in this case would be somewhere in the ballpark of 1 volt. If we had 1 volt drop across a wire with a milliohm resistance, the current flowing through it would be incredibly high. And effectively, the wire is just going to get really hot and you're probably going to catch something on fire. Okay. For those of you who have ever had to change a battery or something like that in a car, or try to jump off a car, like this is one of the reasons why you have to be super duper careful to make sure that everything is connected correctly and that you're using appropriately sized jumper cables, because if you don't, the jumper cables literally can't handle the amount of current that's causing the energy in one battery to flow into the other one to jump it off. And that's why you see all kinds of sparks. And every now and then you might see a fire if people aren't paying enough attention. So effectively, just to recap here, whenever we have two voltage sources in parallel and they have the same voltage, everything is a-okay. Realistically, you could just treat it as if it was a single voltage source. Wouldn't change the circuit at all. Whenever you have two voltage sources in parallel that do not have the same voltage, we cannot analyze that system. So now let's talk about current sources. Let's start with current sources in parallel. So to provide you guys with some context, let me ask a question that maybe I should have asked on the second day of class. How many of you guys have ever seen a physical current source? Like, is that something you can't go buy it at Walmart or anything like you can batteries and stuff, right? Yeah. So a current source is usually a rather expensive electrical device that's used in laboratory settings. We can approximate current sources, and really this is just what a laboratory grade current source is made of, is a bunch of transistor circuits and all of that kind of stuff. So for those of you that go much deeper into electrical engineering, particularly those of you that take our junior and senior level courses on integrated circuit design and all that kind of stuff, you'll see current sources in parallel very regularly, because that's literally just placing two transistors that are biased to behave like current sources in parallel. For the overwhelming majority of you, this is just an exercise for this class. You will never actually see anything like this. Okay. So let's say that I have the following system where I have some DC current source IDC1, direction up, some resistor R like so, second current source IDC2, direction up, and lastly, a current source IDC3, direction down. I am going to choose to make the direction for my resistor current IR as down. And what I'm going to do is I'm going to apply Kirchhoff's current law at the top node, where currents that are entering are positive and currents that are exiting are negative. So in applying Kirchhoff's current law here, we would see IDC1 minus IR plus IDC2 minus IDC3 is equal to 0. Once again, I'm just going to have the resistor quantity, current in this case, on one side of the equal sign. So that's going to look like IR is equal to, and I'm going to leave all of the sources on the other side so that we can see effectively what our resistor sees. So applying Kirchhoff's current law here, we would see that IR is simply IDC1 plus IDC2 minus IDC3, or some equivalent DC current source that is just a combination of those current sources. So the rules for that combination are, if the currents are flowing in the same direction, they add together. If it's flowing in the opposite direction, you subtract it. So extremely similar to what we saw with voltage sources in series. For implementation's sake, generally speaking, how I tend to approach this is, if I'm trying to come up with an equivalent current source direction up, then I give all of the current sources that are direction up a plus sign, and I give all of the current sources that are direction down the minus sign. If I'm trying to find an equivalent current source with a direction down, give all of the ones pointed down the plus sign, give all the ones pointed up the minus sign. So the result depends on whether you want a current source up or a current source down. Okay, so current sources in parallel, fairly straightforward. Now let's look at current sources in series. And this is, again, something that, for those of you that go further into electrical engineering, you'll see in the development of transistor circuits, particularly what's called a cascode current source, or a cascode current mirror. I know that means nothing to any of you right now. That's perfectly okay. But if you want to know about it, you can give it a Google, or you can watch my shitty YouTube channel. So current sources in series. So let's look at a very simple circuit. So let's say that I have a 2 amp source and then a 4 ohm resistor, and then another 2 amp source. So if I applied, and I'm going to call the resistor current as this current flowing from left to right. So if I apply KCL at the top left node, where currents flowing into the node are positive. The current flowing into the node is equal to the current flowing out of the node, will be the easiest way to do it. We have 2 amps flowing in, IR is flowing out, so we have 2 amps is equal to IR. Easy peasy. Things are connected in series, not that difficult. Very similar thing for KCL at the top right. Okay. So IR is flowing in, 2 amps is flowing out, so we're okay. And then let's do over here, KCL at the bottom, 2 amps is flowing in, 2 amps is flowing out. So all of these things can be true concurrently. So in a situation like this, where both of our current sources that are connected in series have the exact same value, 2 amps in this case, everything works out completely okay. And realistically, we could just replace those 2 current sources with a single 2 amp source, and we would have effectively the exact same circuit. But if I had a situation like this, where I have a 2 amp source, my same 4 ohm resistor through which a current IR is flowing, and then now I put a 3 amp current source on this side, KCL at the top left would give me what? So 2 amps is equal to IR, the exact same result as we got previously. If we do KCL at the top right, what do we get? 3 amps is equal to IR, which is problematic because now we have IR having 2 different values. So IR is equal to 3 amps. And if we do KCL at the bottom, we wind up getting 3 amps is equal to 2 amps, which obviously cannot be true, because in order for that to be true, or I guess a better way to put this, in order for this circuit to work as we've drawn it, charge would have to be created somewhere in this circuit, right? Because that's the only way that we can have 2 amps flow into a node and 3 amps come out, is that enough charge is being created at that top right node to justify the 3 amps flowing out. Can charge just magically be created? Not according to the law of conservation of charge. So we can't have a situation like this. So much like with voltage sources connected in parallel, if we have current sources connected in series and they don't carry the same current, we have to just stop. There is no way for us to analyze this circuit. Okay, so how do you all feel about source combinations? Fairly straightforward. This is something that we'll use periodically in order to simplify circuits and all of that kind of good stuff. Now for the much more interesting things, in my opinion, let's talk about the concepts of voltage and current division. So let's start with voltage division. So voltage division is a tool that we can use to speed up the calculation of voltage drops across resistors for now. We can also use it for inductors and capacitors and all that kind of stuff later, wherein we don't actually have to bother finding the amount of current flowing in our system, but it only works whenever we have resistors in series, or we can make things look like we have resistors in series. So let me explain what I mean here really quickly. So let's say that I have a network that is part of some larger circuit that contains multiple resistors connected in series. For what it's worth, this derivation is incredibly similar to what we did on Friday in regards to explaining why resistors in series combine the way that they do, okay? So let's say, and this is a very important thing, that the voltage drop across this network containing all of these series resistors is a known quantity, right? I'm going to assume that there is some current I flowing through this series resistor network. And here the polarities are incredibly important. I'm going to assign my resistor voltage polarities such that the current I is flowing into the positive polarity terminal. So this would be V1, here's V2, all the way out to this voltage, V sub N. So, so right now, this looks identical to what we did on Friday. It's going to continue to look identical for another couple of seconds here, okay? So if I apply Kirchhoff's voltage law to this system, I will have V known is equal to V1 plus V2 all the way out to V sub N. Using Ohm's law, I could then say that this is I times R1 plus I times R2 all the way out to I times R sub N, which would be a common factor of I multiplied by R1 plus R2 all the way out to R sub N. And from this, I could say that I is simply our known voltage divided by that series combination of all of those resistors. Okay. So if I wanted the voltage drop over just the resistor R1, which I'm going to call that V1, well, using Ohm's law, V1 is nothing more than I times R1. So substituting in I, we would wind up getting our known voltage multiplied by a ratio of resistances, where R1 is in the numerator, and then that series combination of all of those resistances is in the denominator. In general, the voltage drop across the kth resistor in series, so this is just whichever resistor we are interested in, I'm calling R sub K, is going to be our known voltage across the entire network multiplied by a ratio of R sub K all over R1 plus R2 all the way out to R sub N, or V known times RK over REQ. So let's work a couple of quick examples here to kind of see how this can be applied. We're going to start with relatively easy cases. So let's say that I have a 10-volt source connected to a 5-ohm resistor, a 3-ohm resistor, and a 2-ohm resistor like so. And I want us to find the voltage drop across the 3-ohm resistor, positive polarity on top, and I want us to find the voltage drop across the 2-ohm resistor, positive polarity on the left. So let's start with this voltage V3. So what's my known voltage, or the voltage drop across all of those resistors in series? 10 volts, the voltage that's being provided by my voltage source. What is the resistance of the resistor that I'm trying to find the voltage drop over? 3 ohms. What is my total series resistance? 10 ohms. So just to be clear, that's 5 ohms plus 3 ohms plus 2 ohms. So this comes out to be 3 volts. No need to find the current or anything like that. This should kind of make intuitive sense. The voltage is just going to distribute itself. We know Ohm's law tells us that V is equal to I times R, right? So if the current flowing through everything is the same, then the 5 ohm resistor should take up half of the total voltage, because 5 ohms is half of the series resistance. The 3 ohm resistor should take up 30%, and the 2 ohm resistor should take up 20%, because it's literally just a simple ratio of the resistor I want divided by the total resistance. Okay. For V2, you guys tell me what that equation should look like, just from the jump. 10 volts, 2 ohms over 10 ohms. Okay, so you're 97% correct. So let's explain why you're not the full 100% correct. So when we derived this relationship, notice that the known voltage has the opposite polarity of all of our resistor voltages. Meaning, if we followed a current around that loop, that current I is flowing into the positive polarity terminal of all of our resistors before flowing effectively into the negative through the known up top. So V2 needs to have a negative sign out front because it's the opposite polarity from how we defined things. Okay. So that would be negative 2 volts. So everybody understand why that one gets the negative sign? Yes.
So for the V3 and V2, did you assign polarities or those?
So I assigned them here. It kind of depends on the problem. So if you were just trying to use voltage division as a quick and dirty way to figure out what a particular voltage in a circuit was, you would have the option of assigning the polarities, and I would probably always assign it such that the current would be flowing into the positive polarity terminal, right? And just to be clear, what I mean by that is, if we imagine a current leaving the positive polarity terminal of our source, this current hits the positive polarity terminal, which means we get a plus sign here. The current hits the negative polarity terminal first, which is why this minus sign is here. On exams and things like that, will probably just define the polarities for you. And so you'll need to keep up with things. Does that make sense? Okay. Yes.
Question about the voltage leaving currently 10 volts.
Mm-hmm.
Because it leaves on the positive side, why wouldn't it be a negative current?
So we are making an assumption here, and it is an extraordinarily correct assumption because there's literally no other way that this circuit could work, that the 10-volt source is supplying power to those resistors, because all the resistors can ever do is absorb power, right? So the current leaving the positive polarity terminal is literally just telling us the voltage source is supplying power in the system, under the assumption that the current's flowing that way. Yeah. Okay, so this is a simple application of voltage division. I don't know how many or if any of you guys learned this in Engineering 120, but it probably would have made things a whole heck of a lot easier for you. Now let's blow your mind and just make you flat out mad that we can apply this to more complicated systems and come up with some results as well. So let's say that we have a circuit or something that looks like this. 15-volt source here. Let's put a 10 ohm resistor, 6 ohm resistor, an 8 ohm resistor, and a 12 ohm resistor down here. And let's say that we are interested in finding the voltage drop across these two resistors connected in parallel. I guarantee, well, I can't say I guarantee, if you've been doing your homework, I guarantee you have seen something like this in your web work section. Okay. Now, we could, if we were so inclined, kind of just throw the kitchen sink at this thing. And by that, I mean we could throw Ohm's law at it, Kirchhoff's voltage law, and Kirchhoff's current law, which is probably what you guys have done in the past in order to solve for that pesky voltage there in the middle. However, voltage division makes this a joke. So we know from our last class meeting that a 6 ohm resistor in parallel with an 8 ohm resistor can be combined into a single equivalent resistance, which means from the perspective of that 15-volt source, it just sees 3 resistors in series, which means we can apply voltage division. So in this case, our voltage Vx would just be 15 volts times, and I'm going to do this the laziest way possible. So 6 in parallel with 8 looks like 6 ohms times 8 ohms over 6 ohms plus 8 ohms. And then my total series resistance is 10 ohms plus that 6 in parallel with 8. Plus 12 ohms over here will give me some result. I'll throw it in my calculator here, but it gives it to me in one step, simply by treating that parallel equivalent resistance as part of a series network. So 15 times 6 times 8 over 6 plus 8, 10 plus 6 times 8 over 6 plus 8 plus 12. So I got a voltage of 180 over 89 volts, which is 2.022 volts. So effectively, anytime we can make a network look like a bunch of resistors in series, we can apply voltage division, assuming that we know what the voltage drop across the whole network is. Okay. So that is definitely a trick that you can use on your web works and stuff like that, and you will definitely, I'm not going to say you have to have it in your pocket for the exam or anything like that, but it will definitely help. And for those of you that haven't finished the last homework set, I feel like knowing this will make some of those questions way easier. So, all right, so how do you guys feel about voltage division? This is just a tool to put into your pocket, but it can be pretty damn useful. And you're going to have a lab on it today. Okay. All right, so now let's talk about the flip side of this division thing. Let's talk about current division. And I want to be very clear here. And this is not entirely just my super inflated self of ego saying this, but the way that I'm going to teach you this is better than you have learned in your previous classes for those of you that are repeating Circuits 1. I'm saying that very specifically because what I'm about to teach you is applicable to any number of resistors that are connected in parallel, whereas the way that this is traditionally taught is only applicable for exactly 2 resistors in parallel, okay? So the math is going to look a little bit grosser, but it is a much more powerful form of current division. So let's say that we have a network, part of a larger circuit, containing multiple resistors connected in parallel. So this will be R1, R2, all the way out to some resistor R sub n, like so. And let's say that the current flowing into this network is a known quantity. Since all of these resistors are connected in parallel, we know that they should have some common voltage across all of them. So I'm just going to call that voltage V. And now I'm going to define all of my resistor currents as flowing down like so. So this will be I1, I2, and I3. So that effectively what I'm describing here is some known current flowing into this parallel combination of resistors, and then it's going to split up and flow between those three resistors, right? So the current is going to divide among those resistors. As we will find shortly, it is once again based on a ratio of resistances, just like voltage division, okay? So applying KCL here, I would have I known is equal to I1 plus I2 all the way out to I sub n. And I'm going to change that label from I3 to IN so that it's consistent. I apologize for that mistake. Using Ohm's law, I can express all of those resistor currents in terms of that common voltage V. So that would be V over R1 plus V over R2 all the way out to V over R sub n. Factoring out the common factor of V, we would get V times 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. And then rearranging things slightly, we could say that V will be equal to our current I known divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. Okay. So if I use Ohm's law, I could say that my current I1 is just V divided by my resistor R1. And another way to think about this would be V multiplied by a factor of 1 over R1. So that when I substitute in my relationship for V, I wind up getting I known times 1 over R1 divided by 1 over R1 plus 1 over R2 all the way out to 1 over R sub n. This is how I would like you guys to remember it. However, this is really just I known times the equivalent parallel resistance divided by R1. And then we could generalize this for any individual resistor in that parallel combination by replacing the subscript 1 with a subscript k. So let's put this into practice. So let's say that I have an 8 amp current source connected in parallel to a 6 ohm resistor and a 2 ohm resistor, like so. I'm going to define the current flowing through the 6 ohm resistor as down, and I'm going to define the current flowing through the 2 ohm resistor as up, just so that we can pay attention to a couple of things. So, using my equation from above, the current flowing through my 6 ohm resistor would be my known current of 8 amps times, in my numerator, I will have 1 over 6 ohms. And then in my denominator, I will have 1 over 6 ohms plus 1 over 2 ohms. And if I throw that into my calculator, I believe I should get 2 amps. Let me think. So 1/6 over 1/6 plus 3/6 is 1/4 times 8 is indeed 2 amps. For I2, going to be something pretty similar. 8 amps times 1 over 2 ohms divided by 1 over 6 ohms plus 1 over 2 ohms. But I need to remember to include a negative sign here because my 2 ohm resistor is flowing opposite direction, opposite the direction that I would expect, right? So if we look at how we define things beginning, I known flows in, and then it splits up and flows down through all of those resistors. Well, I2 is flowing up in the opposite direction, so we need to include the opposite sign. For what it's worth, another way to think about it, if we put the positive polarity terminal at the head of our current source arrow, the 2 ohm resistor is flowing into the negative polarity terminal, and so it gets a negative sign. So this is simple current division. Now let's complicate things slightly and see what we can do with it. So this is a problem that I really like. And so something like this usually winds up on the test somewhere. Let's say that I have a 5 amp source like so. Here's a 10 ohm resistor. Here's a 6 ohm resistor. 4 ohm resistor. And then an 8 ohm resistor. And I'm interested in the current flowing through my 8 ohm resistor. So I want us to look at this really quickly, okay? So the way that I derived current division a few minutes ago, we had a current source or some known current flowing into a network that contained only resistors connected in parallel. If you look at this network, there are 4 resistors and none of them are connected in parallel, but we can still actually wind up using current division. So what I mean by that specifically is the current we're looking for, I8, is the current flowing through that branch containing a 4 ohm resistor and an 8 ohm resistor in series. But if we combine those series resistances, that branch would be in parallel with the 6 ohm resistor. So our current I8 would be 5 amps times, so the total resistance of the branch that I'm looking for the current through is 4 ohms plus 8 ohms. Then down here in the denominator, I have my 1 over 6 ohms plus the same 1 over 4 ohms plus 8 ohms. And that should come out to be, so let's see, 5 times 1/12 over 1/6 plus 1/12. I bet it's going to be a third of 5, so 5/3. So I made the numbers too easy. Yep. Fantastic question. So the 10 ohm resistor did not show up in this equation. Can anybody other than me explain why? Exactly right. So the 10 ohm resistor is in series with the 5 amp source, meaning that all 5 amps flows through the 10 ohm resistor before it sees that parallel network and is allowed to split. So the 10 ohm resistor doesn't show up because it doesn't split and flow through the 10 ohm resistor. All 10 amps flows through it, or 5 amps, excuse me, flows through it. Does that make sense? Yeah. All right. So we have talked about source combinations for both voltage sources and current sources. You have now learned about voltage division and current division. Yes, ma'am. So if we wanted it through the current flowing through the 6 ohm resistor, we would just put 1/6 in the numerator. That's exactly correct, Faith. Thank you. All right, so I'm done ranting at you guys about circuits related things for today. So you've got a mini lab and also an in-class assignment. And as per usual, I would encourage you to do the mini lab first.